Hello everybody, today we'll be going over related rates, that's with an S. Calculus is fun side, so this is where this is the one thing I love about calculus. I've been talking to a lot of people at school, they also love related rates, so I decided to cover it today. I think one of the main ways you can do related rates, how to learn it, you gotta just do some problems. You got to know how to find the derivative. Implicit differentiation helps because that helps you get into the whole idea of dy over dx or dx over dt. Differentiating something other than x. So this is one that's used a lot. Air is being pumped into a spherical balloon at a rate of 8 centimeters cubed per minute because it's a three-dimensional object. Determine the rate at which the radius of the balloon is increasing when the diameter of the balloon is 20 centimeters. So let's start off with this problem. First of all, we know something. If you've taken Math 2, or in this case geometry, and probably trigonometry, you should know what the area of a sphere is. Not area, I mean volume. The volume of a sphere is 4 pi over 3 times the radius cubed. Now here they said the diameter is 20 centimeters. We know we can always change that because the diameter is twice the radius. We know the radius equals 10. Now if we go back to the problem, we know that air is being pumped into the balloon at a rate of 8 centimeters cubed per minute. So if we know the rate of change of the volume, we know that is the derivative. So we can go over here, we can say derivative, I'm just going to use the apostrophe to say v prime equals, and we go back here, 8 centimeters per minute. So we'll just write v prime equals 8. Now what we want to know is the radius is increasing, the rate of the radius increasing when the diameter is a given amount. So we want to know r prime. And how do we do that? Well, we need to find an equation that has r prime in it. And one thing that does have r prime in it is the derivative of this equation. Now this is where implicit differentiation comes in. We're going to differentiate all of this to something like t equals whatever, but that's what the prime is saying. So v prime equals v, this should be a d, back there, dv for dt, same thing with r prime. We're just differentiating it to a variable other than the ones that we're using right now. So let's differentiate this. So we got v prime equals 4 pi over 3 times, let's differentiate this. We know this was a constant, so we can just leave that out. 3r squared. And because we're not differentiating with respect to r, we're doing it with respect to something else, you also have to include the r prime chain rule. And now we got v prime, we got r prime, we want not r prime, we have r, we have v prime, we want to find r. So what we can do, simplify this a little, 4 pi r squared times r. Oh, and if you noticed, if you know the surface area of a sphere, it actually equals this. So the derivative of the volume of a sphere is just the surface area times the derivative of the rate of change of the radius. And the same thing works for a circle, just pi r squared. That's the rate. That's the circle, and dr over dx this just equals 2 pi r times rate of change for the radius. So now you know that volume, the derivative of volume is its surface area times rate of change for its radius, and it works with circles as well. Derivative of the surface, not surface area, just area, is equal to the circumference times the derivative of the radius. That was something fun that you might be able to, that might help you. So let's go back here. Now let's just plug in everything. Or let's just simplify first, that will be a lot quicker. Prime 4 pi r squared. So let's just erase this t because we're not going to need it. Now you should know that for all the problems that we're differentiating them to something else. So r prime equals equals 8 divided by 4 pi times squared, 100. Cancel this out, cancel this out. This is a 50, this is 1, this is 1. The answer should be 1 over 50 pi. But we're forgetting something. We forgot our units. We have our given radius as 10 centimeters. Our volume, rate of change for volume, is centimeters cubed over seconds. And the rate of change for the radius is centimeters over seconds. So now we have our answer. If you forget your units, things will go wrong. Unless the problem specifically says there's no units, then you should be fine. Then if there are units mentioned, you have to write your answer with the units. Otherwise, it's fine. That was problem 1. Let's go over to problem 2. Problem 1b, actually this one has 2 parts. Determine the rate at which the surface area of the balloon is increasing when the volume is 24 pi. So I made this one a little bit harder. You could have just thought that radius, but I got a problem where you have to find the rate of change of the surface area. Luckily, we know that the rate of how to find surface area. Surface area is 4 pi r squared. And let's add in some information that we know. The volume is equal to 24 pi. And we know the rate of change for the volume is equal to 8. So what can we do with this? We don't have r mentioned. We know how to find r, because as we saw before, volume is 4 pi divided by 3 r cubed. So what can we do with this? Well, we can solve for r, so we can replace it in the equation. And we should get r to the power of 3 is equal to 3v divided by 4 pi. And that just means radius equals, now we see it's very messy. But once we get to the end, we should get something with radicals, and you'll see 3v divided by 4 pi. Okay. Now, let's plug this in. Oops, that's very tiny. That's right, a little bit bigger. Area, if we see what we wrote before, it's equal to 4 pi, let's just put this in parentheses, 3v over 4 pi, the power of 2/3. Let's just do that so we don't have to write cube root then squared, or squared then cube root. So now we see that our entire thing is defined in terms of volume. And now if you're given only the volume, this is how you can solve for the surface area. So let's differentiate this. This one shouldn't be that bad. Also, let's just, as habit, let's just write that we're looking for the area, the derivative, the surface area. That's a question mark. A prime equals 4 pi times, okay, so power rule, 2/3, 3v over 4 pi, and this is the power of negative 1/3, and this is all multiplied by 3v prime. Sorry that my v's start looking like y's. V prime over 4 pi. 3v prime over 4 pi. So we can now substitute. This is going to be a lot of fun. What we first do is cancel these out. So we have something a little bit more manageable. A prime equals 2/3, 24 prime, so 72 pi divided by 4 pi, power of negative 1/3 times 3 times 8. Now we can just start canceling stuff out. This goes to 18. So that result itself. Now this cancels each other out. This becomes a 4. This goes to 1. And our answer is 4. Let's just not, we don't need to write that. We can just write divided by cube root of 18. And I don't think you can simplify that any farther because 18 is 3 squared times 2, not 2 cubed times 3. So, and we need our units. Units for rate of change of surface area is, well, surface area. Why am I writing a pi? This should be meters squared per second. So that's our answer for this one. So that's saying you get 24 pi, given the fact that we're inflating the balloon at 8 centimeters cubed per minute. Oh, you notice what's going wrong? This thing is in terms of minutes, so this thing also needs to be in terms of minutes. And what we can do now is go back to the previous one, solve that problem. So the answer to this one is meters squared per minute. And let's just quickly fix this. This is the one with the radius. This should also be centimeters per minute. Okay? So given when the balloon is 24 pi, we're going to get 8 centimeters per minute, cubed per minute. That's the rate of change of the volume. This is how fast this is the rate of change for the surface area. I think we can go on to the second problem. Let's go. Yes, a fun one. This is called the baseball diamond problem. Is it this one? No, this is 2B. Let's go to 2A. So, a baseball diamond is 90 feet square. Let me fix something. Just turn on the laser pointer. Okay, so the baseball diamond is 90 feet squared. That means each length is 90 feet. So a person is running from home base. They get over to first base, declared safe. Now they're going to start running. They're moving at about 30 feet per second. So for this problem, we're assuming it's 30 feet per second. we want to determine how fast he is moving away from home plate when he's 30 feet away. In this case, we're going to say he's 30 feet away from first base, like about here. And then we're also going to figure out how fast he is moving away from third base, when he's 30 feet away. And when you see this, you're going to know something a little bit weird, but it will make sense. So, determine how fast he is moving away. He's 30 feet away. So let's draw a baseball diamond. Let's make this. It will become a little bit bigger, a little bit smaller. Ah, yes, a very bad baseball diamond. Well, let's assume these are all right angles, regardless of how bad they look. There's a person running over here. He's about 30 feet away. So this distance is 30. We know this distance is 90. So what could that say about this one? This is the diagonal. And this is how far he is away from home base. So we're going to write H here, 1 here, 2 here, 3 here, just to show what we're doing. We're moving this way at 30 meters per second, 30 feet per second. Yeah, 30 meters per second would be very fast. This man is practically like running as fast as a bicycle. So, let's go back to the problem. What do we know about this? This is a right angle. These two aren't. This is a right triangle. We know that we know how to find the length of the hypotenuse. This one. C equals the square root of a squared plus b squared. That's just the general formula for this. Now let's see what we can do. We want to find C derivative. We know that A derivative, we're going to call this A, B, and C. Let me just draw the triangle out here. C, A, B. We know that A derivative is 30, and A is also 30. What we also know is that B is 90, because that's this part. This is B, this is A, this is C, just to show it back here. So, what can we do with this? Well, we can try solving. We know B is going to be a constant, so when we write this out, we just change this a little. This is going to be 810. Ooh, I mean 8,100. Very bad mistake of mine. So erase this. And now we can start differentiating. So, C derivative is equal to square root. Ooh, did this wrong. We're going to have to use chain rule on this. So first we're going to start off this part. A squared plus 100. This is going to be multiplied by half, because I forgot to write that over there. But then it's also going to be multiplied by the derivative of this, which is 2a dash. Because we had to chain rule this as well. So if we start working on this, well, what do we know? We know a dash is 30, a is 30. We can start plugging that in. So C dash is equal to, we're just going to write this out into a much simpler way. A times A, these are both 30. That 2 is from the 1/2. Now this should also be, this should be 900. 100. 2's cancel out. And the derivative is going to be 900 divided by 10 root. Let's just do a quick addition. This is 10. This is 10. What did I do wrong? This. This whole thing is going to be root 9,000, which is also going to be equal to 900 divided by 30 root 10. Cancel these out. This is a 30. We go over to the side. We can write out our final answer. The rate of change for the hypotenuse as A increases at the rate of 30 feet per second. When he's 30 feet away, is 30 divided by root 10 feet per second. Okay. I'm going to just zoom this all the way out so you can see what we did. We go back over here, our units are correct. Distance should be changing feet per second. We use feet per second for the whole thing. Now, let's go on to the last problem. 2b. Now we're going to figure out how fast he's moving away from third plate. So when he's 30 feet away. So let's write this out. Let's draw this out again. This time we're using a different triangle. This is going to be our A, our C, our B. This is home base. This is third. This is first and second. Now, what do we notice about this? Because now the runner is moving towards one of the endpoints of the triangle. 30 feet per second. 30 feet per second is only the speed. But now as this distance is going to be smaller, A in this case is actually 60 feet. B is 90. We want to find derivative of C, given the fact that we know what the derivative of A is. In this case, A will be negative 30 for one reason. We're actually moving in the opposite direction of where we want to. We're moving closer rather than farther, meaning our velocity is going to be negative. And when you find the answer, you're also going to notice that it will be appropriate to what we're finding over here. Let me just change this. This is away from first base. That should clear up some confusion. This is not 30 feet away from second base, this is 30 feet away from first. So let's find our equation again. I think we can just go over to this one. So our derivative will be around the same thing. We still know that C equals root of A squared plus B squared. B is equal to 90, which means root of A plus 100. The derivative of this is now going to be equal to 1 over 2 root A squared plus 8,100 times 2A prime. There we go. So this is where we were before. We just have one slight change.
which is now a prime is going to be negative, not positive. Which means once we plug this all in, 2, this is going to be negative 2 times 900. This is going to be 2 times the root of 9,000. We should get the same answer as before, except it's now negative 30 for root 10 feet per second. And we still have room. There we go. So why is the feet per second negative? And this is why it makes sense. Let's say we're over here. This is a minus some amount. This distance d is going to be less than this distance c. So if we look at it, the feet per second is just saying that the distance of the runner from third base is actually going to be reducing as we approach second base. I mean, at first base, it's actually the farthest away, the farthest distance possible on the square. So as we move towards second base, it's only appropriate that it should start getting smaller again. Okay, I hope you enjoyed learning about related rates. This is calculus, this fun side, at least until you get to other stuff, like series. Like and subscribe if you like this video. Leave a comment about other stuff I should do for this. Share this with friends who need help with related rates. I know some people I might send this to. And I'll see you soon. Bye.